Today, we're diving into a landmark 1997 paper by Robert Tibshirani that introduced a seriously powerful tool for survival analysis. Imagine you're in a situation where you have a ton of data, but you're trying to figure out which pieces of information are actually telling you something important. This paper offers a really elegant solution to that exact problem.
Okay, so here's how we're going to break it down. We'll start with the core problem in survival analysis, finding the signal in the noise. Then we'll introduce the Lasso's clever solution. We'll get into the math just a bit, see how it gets tuned, put it head-to-head against some older methods, and then we'll wrap it all up with the big picture.
All right, first things first, let's set the stage. Picture this. You're running a clinical trial, and you've got dozens of variables for each patient. We're talking age, blood pressure, specific genetic markers, the whole shebang. So how on earth do you figure out which of those are the real predictors of survival and which are just, well, random noise? That is the fundamental challenge, right? The standard tool for this job has always been the COX proportional hazards model. It's great, but it has a classic problem. What do you put into the model? If you just throw everything in, you get a mess. So selecting the right variables is absolutely critical. So let's move on to the solution that Tibshirani proposed. And it's this really ingenious twist on that standard COX model. It's a method designed to create what statisticians call a parsimonious model. Basically, the simplest model that still gets the job done. Now, what's so cool about this is the constraint. I want you to think of that little s as a kind of budget. The model can't just make the coefficients, the importance of each variable, as big as it wants. No, it has to spend its budget, and it has to spend it wisely on only the most important, most predictive variables. And here is the magic of the lasso. This isn't just about making some coefficients smaller, which other methods do. Because of the way this budget is set up, it performs automatic variable selection. It literally forces the coefficients of the least important variables to be exactly 0. It's like the model is saying, nope, this one's not worth spending any of my budget on, and just drops it entirely. This creates a much simpler, much easier to understand model. So how does this all work under the hood? Let's take a quick peek at the mathematics. Don't worry, we're not going to drown in equations, but getting the core idea here is really crucial for understanding why this thing is so darned effective. Okay, the heart of the COX model, and the Lasso version of it, is this thing called the partial likelihood function. It is the engine that makes the whole thing run. So let's break it down piece by piece. So what you're really looking at is a ratio. For every single time an event happens, say a patient has a relapse, we calculate this. The numerator on top is basically the risk score for the one person who just had the event. The denominator on the bottom is the combined risk score of everyone who is still in the study and could have had that event at that exact moment. And that group in the denominator is called the risk set. By only including the people still at risk at each specific failure time, the model inherently and very cleverly accounts for the sequence and the timing of events. This is fundamental. It's not just about if an event happens, but when it happens. And this structure is how the model understands that. All right, so we have this powerful constraint, this budget. But that leads to the obvious question, right? How do we pick the right budget size? Let's see how the paper solves this. I mean, if you make the budget too small, you might throw out important information. But if you make it too big, you're not really simplifying the model at all. So you need a way to find that Goldilocks value, not too big, not too small. And the paper proposes this really neat data-driven method to do it called generalized cross-validation, or GCV for short. Now, you don't need to compute this by hand, but the idea behind it is key. GCV is basically a balancing act. It looks at how well the model fits the data, that's the L of S part, and it weighs that against how complex the model is, that's the P of S part. It's designed to find the budget value S that gives you the best predictive performance by penalizing models that are just too complicated. Okay, let's look at a concrete example from the paper. They used some lung cancer data. And what you see here is a plot of the GCV score. Our goal is to find the lowest point on this curve, because that's our sweet spot. And right here, you can see it bottoms out at about 0.45. That's our optimal budget. And this is where it all comes together so beautifully. We take our chosen value of 0.45 and draw a vertical line. Now look where that line crosses the paths of all the different coefficients. Bam. Only one variable, something called the Karnofsky score, has a non-zero coefficient. Every single other one has been shrunk all the way to 0. The Lasso just told us what matters most. So, this new method seems pretty awesome, but is it actually better than what people were using before? Well, the paper puts it to the test, pitting it directly against the most common method at the time, which was called stepwise selection. And just look at these numbers. This is from a simulation where there were a few variables that had a big effect and a bunch that had zero effect. The Lasso's error, that's the median MSE, is 0.26. That is dramatically lower, meaning way more accurate, than stepwise. And look at the last column. It was much better at correctly identifying the useless variables and setting them to zero. And if you want visual proof, this is it. These box plots show you just how stable the estimates are. Now, what's really interesting here is the bottom row. You can see so clearly how the Lasso model does the best job. The estimates for the true effects are right on the money, and all the noise variables, well, they've been successfully crushed down to zero. It's just a cleaner, better result.
Okay, so let's move to our final section and just wrap up what makes the Lasso COX model so powerful and maybe what to keep in mind when you're using it.
So the crucial point here is that the Lasso really delivers on two fronts. It's accurate, but it's also interpretable. It's a stable, data-driven way to achieve parsimony. It's like a one-stop shop that does both variable selection and estimation all in one clean, elegant step. Of course, no method is a silver bullet. You still have to do your due diligence, right? It's really important to standardize your variables first to make sure the penalty is applied fairly, and you still have to check the underlying assumptions of the COX model itself. Think of the Lasso as one incredibly powerful tool in your analytical toolkit. And honestly, the paper's own conclusion just nails it. It perfectly captures its impact. It offered this robust, elegant alternative that, really, has become a cornerstone of modern statistics ever since. And that leaves us with a final thought, one that's maybe even more important today. The Lasso strikes this amazing balance between performance and simplicity. And it makes us ask a really important question. When we build these complex models, what do we value more? A black box that's maybe a tiny bit more accurate, or a simpler model that actually tells us a clear story? Thanks for joining this explainer.